All right, next lecture is, I think, corresponding to problem number 7, and this is about momentum and collisions. So we talked a little bit about angular momentum, but let's start with linear momentum. And similar to angular momentum, it's just m times v equals p, represented by a p is momentum. And momentum is conserved as long as there is no external force. That's kind of the big idea, is that m1 v1 equals m2 v2. And with this equation, we are assuming that there is no external force that's brought in, no like shocks to the, no like other sources of energy or force that gets put into the system to increase extra like speed or whatnot. So if there is, however, a change momentum, we use the equation delta p equals the integral of f dt. And this makes sense because force is mass times velocity, or mass times displacement over time squared. Whereas momentum is just mass times displacement over time, which is velocity. So we can see that to integrate to get from f to p, we would need to multiply this equation by a t, so that's how we get the integral. So now moving on to like types of collisions, we know that there are basically 3 types of collisions. There's elastic, and an elastic is where there's no deformation at all, like the two objects colliding like bounce off of each other completely, and there's not really any scenario where this is entirely true except on like molecules level, but the main idea is that we conserve momentum after and before the collision, and also the amount of kinetic energy in the system is also conserved. And that's elastic, and then we have inelastic, which is just when kinetic energy is not conserved, and that's when the two objects are basically like deformed, or they like basically alter each other in such a way in which kinetic energy is not conserved. And then lastly, we have perfectly inelastic, and this is when the two objects stick to each other. So it's where we have object 1 and it collides with object 2, and then after we get just like something like this. They stick together, and in this scenario it's just momentum is still conserved because there's no external force, but also kinetic energy is not conserved obviously, but there's just an easier formula given that these two are now going at the same velocity. So knowing that, let's look at what problem 7 has to say. Okay, this has 2 cars. It's probably easier if I draw it. A going this way, and it's moving, and there's B, which has a compressed spring, and it's stationary. So B is just sitting there, and it has a compressed spring storing a lot of energy, storing elastic potential energy, and it is not being released yet. It's just stored as potential energy. And basically they're going, and then after they collide, they start moving in opposite directions, and this spring gets compressed. It gets loosened. It like releases all its energy, and basically this spring uses its energy to push A and B farther apart. So before we really look at what happens, it's basically we just get the idea A is going, and then all of a sudden it unlocks the spring compression, and then they both go like flying in the other direction with a lot more velocity because of the energy that the spring put in. So this question asks us to compare kinetic energy and momentum before and after the collision. And so the first thing we like to think of is that kinetic energy in the system First of all, the collision is pretty elastic because it doesn't deform each other or anything. And second of all, we are inputting a huge amount of energy, of kinetic energy into the system. This before was potential energy, but after the spring gets released after the collision, it gets converted into kinetic energy. So for that reason, it's pretty clear that kinetic energy will increase, basically eliminating answer choice D and E. Kinetic energy increases because we are converting elastic potential into kinetic energy, and no other kinetic energy is really lost. So now let's look at momentum. The idea here is that momentum, if there was no spring here and if they just collided, then momentum would be conserved. It would stay the same because they're going and then they hit m1v1 equals m2v2. But the thing with this special scenario is that we have a spring here that as soon as they collide, it exerts a force on A, pushing them apart, which is an external force basically to the system, which is going to vastly increase the magnitude of momentum because there is a force acting on these two objects at the time of the collision. So delta P is going to be greater than 0 because the force pushes them apart, pushes them at greater speeds, meaning greater momentum. So kinetic energy increases and momentum will also increase. Answer choice C.